In a previous video, we talked about how we could use vapor-liquid equilibrium diagrams in order to figure out the different compositions in a two-component gas-liquid system, right? And so for example, this benzene toluene diagram, the bottom black line here corresponded to the boiling point, and the top line here corresponded to the dew point, all right? And so these diagrams are convenient to use if you just wanted a, sort of qualitative estimate of what the mole fractions were in the liquid and vapor phases. But what if we wanted to be more quantitative? What if we wanted to get a precise estimate of what those mole fractions were? Or, for instance, what if we wanted to develop this VLE diagram for a completely different chemical pair? How would we do that? And so in this series of videos, we're going to discuss the math that you need to use in order to develop these VLE diagrams. Okay? And so, how is a TXY VLE diagram calculated? Okay? All right? And so, to develop those boiling point and dew point lines, otherwise known as the liquidus and vaporous lines, we're actually going to use two different equations. All right? So liquidus and vaporous lines represent, respectively, the T-boil and T-dew calculated from two different equations, okay? And I'm going to go through what those two equations are. The first equation that we're going to use is that combined form of Dalton and Raoult's law, right? And so let's say we're doing this for the benzene toluene system. The first equation I'm going to use, which is going to calculate that boiling point liquidus line, is going to come from the combined form of Dalton and Raoult's law, right? Where we have pressure is going to be equal to the mole fraction of benzene in the liquid phase times the vapor pressure of that benzene at the boiling point, plus the mole fraction of toluene in the liquid phase, and also its vapor pressure at its boiling point, right? And I want to emphasize something here, that even though we're looking at two different components, in the mixture, they both have the same boiling point, right? So there's just going to be one boiling point temperature that we're going to use in this equation, okay? I'm now going to kind of simplify this equation by rewriting it in terms of only the benzene mole fraction, right? Because we know, since it's a two-component system, that our X toluene is also equal to just 1 minus X benzene. I'm also going to expand out the vapor pressures here by plugging in Antoine's equation, right? And so I'm going to rewrite this equation like this. So we have X benzene, and then from Antoine's equation, we have our vapor pressure actually has this form, so it's 10 to the, where now we have those experimental constants. So once again, this is just from Antoine's equation, plus T boiling point. All right, and then now I have the right-hand side, 10 of the plus sign, which is going to correspond to all the toluene parameters. here. Let me correct this just so I have consistent notation everywhere. Boil, boil, boil. Okay? Okay, and so in this equation, I'm going to say this is equation 1. Okay? This is the first equation that we're going to use in order to calculate, the pressure values and boiling point temperatures at our different mole fractions. Okay? So that's the first equation. The second equation I'm going to use actually even just stems from the fact that, the sum of the benzene mole fraction and the toluene mole fraction are equal to 1. Okay? And so maybe it'll help out if I just move this down a bit and say, now for calculating the dew point, we're going to use another equation. Right? And so here, we're just going to start with this relationship. What I'm going to do now is I'm now going to invoke Raoult's law to replace these liquid mole fractions with the vapor mole fraction relationships. Right? And so from Raoult's law, we know that our X benzene is going to be equal to the Y benzene times the total pressure divided by the vapor pressure. Once again, this is just from Raoult's law. Right? And since we care about the dew point pressure, our vapor pressure we're going to calculate is going to be at T dew. All right? And then for the toluene term, we're going to do something similar, except now, well, actually, I'll just write Y toluene. Still it's the same pressure, and also it's vapor pressure at T dew. So I'll emphasize here that there's just going to be one dew point temperature, right? Both the benzene and the toluene terms use the same dew point temperature. All right. I'm now going to kind of put this equation only in terms of the benzene vapor mole fraction, and I'm also going to plug in for Antoine's equation. So now I have 1 is equal to Y ben P over the vapor pressure from Antoine's equation, B ben C ben plus T dew, line here, and that's plus 1 minus Y ben over P 10 to the A toluene minus B tol over C tol plus T dew. Okay. All right, and so I'll call this equation 2. And so what I'll point out is from these equations, if we pick for instance, in equation 1, if we pick a certain liquid mole fraction and a certain temperature, we could then solve for the boiling point temperature at those conditions. So going back to our VLE diagram, if we knew the X liquid was 0.4 and we knew that the total pressure in the system was 1 atm, we could then calculate the corresponding temperature that it belongs to. All right, so that's why I'm doing this. And we could do the same thing with the dew point temperature. All right, that would give us this top line. But there's one kind of roadblock here. All right? If we want to solve for T-boil, how are we going to do that? This is not a simple algebraic equation, or it's not a simple linear equation. Right? We have T-boil inside of two different exponents. Right? That's not going to be, we're not going to be able to solve that algebraically. Or even similar in the second equation, our dew point temperature is still inside of an exponent. We can't solve that algebraically. So how are we going to solve for them? Right? If we can't do it algebraically. And so I'll say here, equations 1 and 2 are nonlinear. In other words, how are we going to solve for T boil and T dew? And this is not just a problem that you're going to encounter just in this video. This is a problem you're going to consistently encounter in this course, where you're going to deal with kind of complex nonlinear equations. So how are you going to solve for them? Well, in this course, what we're going to do is we're going to use either Excel Solver or, well, and/or, I would say, and/or MATLAB to solve these nonlinear equations. Okay? So that's going to be our tool of choice.